Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very busy here, so this talk today is about expressive and scalable pub subsystem, how to build it, kind of the underlying basics, how we can actually design such a system. And this is joint, so I'm Jörg Riedewald, I'm with the Computer Science Department at Cornell University, and this is joint work with Eldemers Mingcheng Hong, who has actually interned here during the summer, and Johannes Gerke and Walker White. Now first, probably everybody has already, each of you here has probably heard already about PubSub in one way or another. And PubSub today is essentially mainstream technology. It is supported by virtually all message-oriented middleware and message brokers by major vendors. There's actually also a standard Java message service. And up here, I've included a picture from the JMS tutorial, which basically shows how the JMS version of PubSub works. This is essentially topic-based pub subsystems where subscribers register topics they're interested in, and publishers publish articles or news on that topic or messages in general, and these articles get then forwarded to the interested subscribers. And PubSub has also been and still is a very active field of research. There's a lot of work from 10 years or more ago also on active databases that falls into this broad category, work on event systems. High performance implementations exist like Resubscribe. And there has been also a push to make PubSub distributed and scalable in terms of internet scale processing of events. And you probably also know here Microsoft has also products that support enterprise application integration, and this also is usually supporting some kind of PubSub technology. And then probably everybody has seen already internet scale news services and heard about distributed enterprises which are based on PubSub technology. Now in general, what is PubSub and what will I refer to when I say PubSub in this talk? There are actually many different ways of what PubSub could mean, but in general it always means there's a set of publishers, there's a group of subscribers on the other side, and now the publishers generate data and the subscribers are interested in a subset of that data, or some combination of the data published by the publishers. And in the middle, there's the middleware, which is essentially doing the matching and forwarding the right messages to the subscribers. And if you go to the internet, there's services like pubsub.com out there, and pubsub.com supports a very specific way of doing PubSub. You can enter keywords like, for instance, Big Red, which is the name of the team of Cornell, which is not very successful, unfortunately. But so you can enter keywords, and then similar to Google, now you have entered a subscription. So instead of having a one-shot query, you register the subscription at pubsub.com, and pubsub.com is monitoring. They claim 16 million weblogs, 50,000 news groups, and all SEC filings. So if you're trying to invest in stocks, it might be a good idea also to use that service. Then you can actually get, whenever an article arrives on one of your, that matches your keywords, it will be forwarded to you. Oh. So why is PubSub such a great idea? Why has it taken off so much? Up here, I don't know if you can read it in the back, there's a picture which I took from the Microsoft BizTalk website. And it explains essentially how BizTalk is connecting different applications in a distributed environment. Again, on the left side you have the publishers. On the right side you have subscribers which register their interest in messages produced by the publishers. And now the system is essentially completely decoupling publishers and subscribers. So a publisher doesn't have to worry about how many subscribers are there on the other side, who's subscribing to the messages it produces. It can simply send its messages to the broker in the middle. And similarly, subscribers, they don't have to know who's publishing what and when. They simply submit their subscriptions, and whenever a matching message arrives, they will receive it. So they can easily join and leave the system. And another big point for PubSub has been also that systems that have fairly simple query languages to formulate their subscriptions have shown very high performance. And the example for that is the Resubscribe system, which has been published a few years ago at Sigmod. which essentially takes advantage of index structures, cache locality, and others in order to actually prune the search space when an event comes in so that it very efficiently can be matched with thousands or hundreds of thousands of subscriptions. Now, what is the problem with current pub/sub technology? Traditional pub/sub, which is what I refer to here, only supports a very limited language, and this is the pub/sub that achieves this high scalability. And typically this language is simply, you can formulate some conjunction of predicates of the form where you compare an attribute from an event or a message against a constant. And then you can build very efficient index structures in order to match the different subscriptions with an incoming event. As soon as you have a more complex query, all these systems are not very efficient anymore in processing multiple queries at the same time. Now if we look at existing and emerging applications like stock tickers, RSS feeds, transactions and retail chains, analysis of OS and web server logs, and Dave can probably tell you more about that as well. Then also intelligence community network monitoring, and all these applications, you might not think of them as pub/sub applications, but also you have problems there that there are many publishers of information. There might be potentially hundreds or thousands of queries, and now you want to efficiently match the publications with the queries in the system. But for many of these applications, you actually need much more than simple comparison of a single event or message against a filter. And for instance, let's take one of the fairly well-known examples from the research literature also, stock monitoring. So there are some examples for queries that one might be interested in. And in general, if you look at websites where stock monitoring is supported and stock trading at internet scale in general, you will see there essentially patterns that analysts are looking for. Typical patterns are, for instance, M-shapes, looking for some ceilings or for some baselines where a stock makes a movement up or down. And all these are actually time series patterns which you describe. And all these time series patterns are more complicated than what a simple comparison on a single event on simple constants could actually support. And when we look, for instance, at these two examples here, the first one is a very simple query. We look for pairs of stock values from the same company, and now the second one should be 5% above the first one. So now you not only have to keep track of there has been some event before and now I can forget about it and match a new event, you have to actually keep track of which company the previous stock value was on and what was its price actually, in order to determine that the next one is actually on the matching company and has a 5% higher price. And this query even requires a potentially unbounded number of matches when you're looking for a monotonic sequence. And the last query actually contains an aggregate. So instead of only taking events that are coming in and just kind of remembering relevant events, we want to be able also to produce new results over the incoming events. Let's look at some other examples. So in general, when people look at RSS feeds, you think of it also probably more of a pub/sub approach where you register an interest. I want blogs about a certain topic. I want news about a certain topic. But now what about queries where you want to actually look at the structure of how different blogs cite each other? It's very common in blogs that there's one writer who copies part of another writer's article and references it. And now you want to analyze that structure, kind of keeping track of how some information was actually assembled over different blogs and fused together by another blog writer. And here we have some examples of queries that one might be interested in. And there are many more. And having a more powerful language, one could actually have a system that looks at multiple blog producing sites, looks at the structure of how these blogs cite each other, and then notifies the subscribers when something interesting happens. And something I talked with Dave about, so at the Cornell Theory Center, there's a high-performance cluster of Windows machines. And when you have many machines will fail over time. And oftentimes, there are already indicators that such failures might happen. For instance, for a break-in, you will see there are multiple logins that failed within a certain amount of time. For hard disks, before they fail, they actually produce more errors. But an error by itself is not a problem because every hard disk has some sectors going bad from time to time. So only by looking at patterns of these events, you can actually really detect that there's a problem without having too many false positives. And so we have started talking also to Dave and his group to see if we can use the technology for monitoring operating system events. So how can we support this kind of query functionality efficiently? And now we want to not only do it for a single query at a time, but potentially for many queries efficiently. So as I mentioned, simple pub/sub is probably not the answer because it doesn't support parameterization. It cannot support queries or subscriptions involving multiple events and patterns. Now let's look at database management systems. A very mature technology, but unfortunately, it is not really built for this kind of application. Because in a relational database system, you expect operators over fixed sets of tuples, and queries are essentially one-shot. And we have exactly the opposite problem here. We have data streaming in, and queries are actually registered. The subscriptions are long-running continuous queries that are registered with the middleware. So then the obvious answer seems, why not use data stream management systems? They're exactly motivated by this problem that databases do not support continuous queries over data streams. But when we look at the existing work on data stream management systems, they have very expressive languages, but there's very little work on making them actually efficient in terms of multi-query optimization and to scale to multiple queries and high event rates. And there's been another big area of work that is related to this kind of functionality that we want to support. And this is the general area of event processing systems. And I include also active databases here, work on triggers and databases. And we can summarize it essentially as there's a lot of work and a lot of interesting proposals there in the research and also implementations in practice. But when we look at what work has been done, there's an unfortunate dichotomy between theoretical and practical approaches, where theoretical approaches often have very elaborate languages. They support parameterization, aggregates, but there's no scalable implementation, and it's not really clear how to do that in many cases. While in the systems work, there's a system prototype, but oftentimes the language semantics are not clear, and there have been also observations in the literature that some of these systems actually have very unintuitive semantics if you look at what these operators are really doing and what a user would expect these operators to do. And there's virtually no implementation that actually supports efficient parameterization in this world of event systems. Oftentimes, parameterization is handled externally. It's kind of similar as if you wanted to compute a join by first computing a cross product and then selecting afterwards, which is not efficient to do. And also aggregates are often handled externally. For instance, in the Snoop system, once a pattern matched, the corresponding events are sent to some other application which is then computing the aggregates for that pattern. And we want to include that in the language. So we want it all. We want precise formal semantics. So we want to exactly know what the query is producing and avoid well-known problems like this one here, which occurs for systems that only use single timestamps for events when they produce composite events. Now if you look at a sequence of an event followed by another event, followed by another event, if we have a right deep expression like this, now you can imagine event E3, if it happens after both E1 and E2, if you now group E2 and E3 together, the end time of that event is after the end time of E1. If you group E1 and E3 together, the end time of that composite event is also after the end time of E2. So now you can regroup, and you can actually prove that for systems that only use a single timestamp for the events, that actually this is an equivalent expression. And this is not really something you would expect from a sequence of events. And I will talk a little more about this later. Another reason for having formal semantics is you want to be able to rewrite queries. Let's say you have a right deep expression which is expensive to compute. You want to translate it into some left deep expression which can be evaluated more efficiently. And for multi-query optimization, obviously we need some kind of formal semantics to be able to tell that we're really computing the right thing after merging expressions together. Of course, we want expressiveness, but we only want enough expressiveness to support the kind of interesting queries we are looking at. And we're aware that there's a performance expressiveness trade-off. So we still want to be able to make pub/sub more expressive, but we want to maintain its scalability in terms of the number of events and the number of subscribers and their queries that are registered at the system. So this is the main motivation for our work. So now in the remainder of the talk, I will first introduce our formal query language, which essentially is an algebra for data streams. And then I will show how we can translate algebra expressions into non-deterministic finite automata, which guarantees that they can be efficiently evaluated. Then I will talk about how we actually implement it in a system prototype, and I will show some experimental results for this prototype. So at a high level, what is our stream algebra? Our system is called Cayuga, so we call this the Cayuga stream algebra. It's essentially a data model for streams of events, plus a collection of operators that take a stream and produce another stream as their output. And these non-deterministic finite automata, which will be used to implement an algebra expression, are essentially also driven by incoming events. See, these automata have states, and edge transitions are driven by incoming events when the corresponding edge predicates are satisfied by an incoming event. And the instance of these automata, which correspond to partially matched patterns in the system, they carry along with them the relevant information from the events that have been matched before. So if you're looking at stock sequences, these instances or patterns that we are matching, every time we make a transition in our automaton, it remembers more about the pattern that has been seen so far and can then return the whole pattern to the user as a final result. And we use aggregates to create new information like average values of stock prices, for instance. So just to make it formal, a stream essentially is just a possibly infinite set of tuples, and the tuple consists of a data part, which is just the same as in a relational database. So you have attributes that have certain values, and then there are two special attributes. That's two timestamps, T0 and T1. T0 is the starting time of the event, and T1 is the end time of the event. We call it the detection time, because that's the time when the event actually happens. And why do we need two timestamps? Why don't we just take one and say that's the detection time of the event? Well, if we look at something like a sequence, or let's first look at a base event. In our stock example, you would say a certain transaction happens at a certain time, so start and end time are essentially the same. So let's say IBM stock sold for $95 at 9:15. Now if we match a sequence of, let's say, monotonically increasing stock prices, that sequence starts at a certain time and it ends at a certain time. And instead of just using the end time, which is the time when that sequence actually happens, we also want to remember the start time in order to avoid problems with the query semantics, which I mentioned before, where actually the sequential composition is not really well defined. So now we have our data model. What are the operators that we want to support? Well, first of all, we want to be able to select interesting events out of our event stream. So we want to support selection formulas, theta, and you can think of them. So in this talk, I will mostly talk about simple conjunctions because we want to leverage pub/sub technology, but we can also handle arbitrary Boolean combinations. And in general, you compare values from an event, like the name, for instance, the value of the name attribute of an incoming event or message, and you compare it to constants. And later on, I will show also a generalization of that. And we allow another type of selection on the temporal values, which is we can query the duration of an event. So if you have a composite event which spans more than a single time unit, you can also query the duration of that event and use that in the selection formula. And in theory, you could imagine any kind of query on the timestamps as well, but for different reasons, so far we only support duration, and one of the reasons is that we want to be shift invariant. So no matter what the absolute timestamps are, the result of the query should be the same based on the relative timestamps. And feel free to interrupt me when there's a question about any of these. So now, all our operators are motivated essentially by regular expressions, and we extend them to make them more powerful. So the first set of operators we have are selection, projection, renaming, which also occur in relational algebra. And what do? They do exactly the same as in relational algebra. Selection applies a selection formula to a stream, and it returns only those events that satisfy this selection. Projection gets rid of data attributes which we are not interested in. But notice that we cannot project out the timestamps because they are necessary for the actual processing of the tuples, and they drive essentially the semantics of our system. And renaming simply does the same as also in relational algebra. You have an attribute whose name was company or price before, and you can rename it into any other name you like. And we need that only for formal reason in order to formally describe the semantics of operators. But for this talk, it's actually not very important. And most of the time, I will simply assume that all operators, all the attributes get renamed into different names so that there's no naming conflict whenever we do something like union or other join operators. And when we look at the corresponding automaton to implement these operators, let's look at an expression where we select on a stream SI, and then we rename the attributes. And I ignored projection here because it's very straightforward, and it looks already cluttered enough like this. Now, when we look at this tuple here, this automaton has a start state, it has a final state. And in this tuple also, for formal reasons, we have a lot of values here because these automata need to support a very powerful language. But for the purpose of this talk, let's only focus on these two middle parameters here. And these are essentially the selection formulas that determine if an incoming event allows you to make a transition from this state to the other state. And also the split in two conditions is actually because of formal reasons. So if you want, it's actually easier to imagine that these two are connected with an AND. So essentially, we only have a selection condition here. The renaming is applied once the event makes a transition from the start state to the final state, and only events that satisfy condition theta can actually make the transition. And just as a brief note, in general, at every state of an automaton, we have a fixed schema, and every event, which is essentially, since all our operators produce streams as output as well, so we produce events as intermediate results. And events in this case are partially matched sequences of patterns we're interested in. At every state we have a fixed schema, and that schema is only affected by projection and renaming, and aggregates as well, but I'm not talking about this right now. And the schema essentially determines uniquely what information these partially matched patterns are carrying around with them until the final state. So the next operator is the union operator. Again, it's the same as in relational algebra or in regular expressions. You have two streams, S1 and S2, produced by expressions epsilon1 and epsilon2. What is the union of these two expressions? We simply take whenever there's an event on either stream, that is part of the output result. And this is what the automaton is computing. So we have an automaton that matches expression E1, epsilon1, and an automaton for epsilon2. And now you can either get from start to final state by satisfying epsilon1 or epsilon2. And the way how f and theta are added is basically just the straightforward construction, what you would expect. Essentially, you go through the automata without any changes, and only on the last step you actually check that theta is also satisfied before you can go into the final state. And you also apply the renaming, which is applied outside this expression in the final step when you get into the final state. Now, the last two operators are actually a little more tricky, but they're also fairly intuitive. And one of them is the sequence operator. Intuitively, what you want to do is you have an event, let's say a certain stock price, and now you want to find the next event that satisfies a certain condition after this event you have seen so far. Let's say after looking at some IBM stock price, you want to get the next IBM event, and now you want to look at some condition. So the condition actually here, that theta, is that you're looking now for another IBM event, and you ignore all the non-IBM events in between. If you're looking for Microsoft stock, you ignore all the non-Microsofts in between. And then once you've found the next event with the corresponding property that theta is satisfied, then you can do computation on that sequence of events. So let's look at an example. For instance, IBM price increases by at least 10 in consecutive sales. So you're first looking for an IBM event, which is this part here. You select all the IBM events from stream S1, and then you want to find the next event from stream S2, which is also on IBM. So you ignore all the non-IBM events, and then you select, out of all these pairs of IBM events, you select those where the price of the second one is 10 greater than the price of the first one. And similarly for the other example here. So you can see that we can handle parameterization very naturally and easily in that model. And Automaton, even though it looks a little cluttered here and a little confusing, it's actually also fairly straightforward to understand. So when you look at this expression, you have an algebra expression epsilon 1, and you want to find the next event that satisfies epsilon 2. The automaton looks like this. We match epsilon 1. Then we are in a state where we are essentially waiting until the matching epsilon 2 event arrives. So we have this kind of filter edge, we call it, which allows us to basically skip over events which are not satisfying the theta condition. So if you're looking for a certain sequence of Microsoft events, so let's say you first found some initial sequence of that pattern. Now you're looking for the next Microsoft event that has a price greater than the previous one. So whenever there's a non-Microsoft event coming in, you just ignore it, following this edge here, until you finally find a Microsoft event, and then you can make a transition into the final state if that stock price satisfies condition theta 3. Otherwise, if you cannot make any transition, neither this nor that one, then the corresponding instance of the automaton dies. And yes, Roger.
What would it be like if I'm looking for all events, like I have n events that have to all happen? What would the automaton for that look like, and what primitive operator would you use to construct some kind of operator like that?
So you want all events with a certain property? Or?
Let's say I give you a list of 5. I don't care about the order, but I want them all to occur. What would the automaton
So you want all. So you have a set of 5 events, and you don't know which order they come, but all of them have to appear, and then you can make the transition to the final state. So for that, we would actually need 5 states. So at each state, we can only match one of them. But then we can do something like encoding, essentially, how many of these different events we've seen so far. We can use an aggregate, for instance, to make sure that we don't see the same event twice and then count it as 2 different events. That's the main thing we need to do. But essentially, we have 5 states, and then you make a transition from one state to the other on any of these 5 events that you're interested in, making sure that once you have made a transition on a certain event, that now you have a parameterization that says if you have made a transition on that type of event before, you cannot make another transition on the same type of event. So you make sure you get 5 different
So you basically implement a counter.
Right, essentially a specialized counter. But we need 5 states for that.
But that doesn't really work if you have the number of events. I want to see n of these before. N of these before I'm done. And n is a parameter, it's not known.
Yeah, so you would have to, so if you know what n's you're interested in, you would have to submit a query for each of the possible n's. Otherwise, if n can be potentially unbounded, then there's no way of specifying it in a way that you can see all these n events actually making transitions. And it's actually also related to the next operator we'll be talking about, which is an unbounded number of this kind of sequence matching. But there you actually lose the intermediate events for reasons of storage efficiency. So just as a quick remark, defining what the next event is in terms of a sequence of events is actually very tricky business, and we looked at a variety of systems and language designs, and there are lots of different ways of defining it. And one of the challenges is there's of course a certain set of properties that you always want to be satisfied for next, but then there's something like associativity, and we actually in some later research in some ongoing research, we actually looked at different models for time and different models for what the next event is in the system, and we can actually show that there are only very few models that make sense. And out of them, some of them support associativity, some of them don't. And then there are, of course, other problems like what I mentioned before. If you only use point timestamps, then you can get some surprising semantics. So you have to be very careful in defining what your next event should be in a sequence of events. But this would be a talk by itself, actually. So we have one way of defining sequence, and the iteration operator is now generalizing it to a possibly unbounded number of matchings of this sequence operator. So it's probably not worth going through the definition here. Essentially, you can imagine it like a cleany plus operator. So instead of only finding the next event with a certain property once, you now keep on matching until a certain condition holds a potentially unbounded number of times. And let me skip that one as well. So let's just look at the automaton right away. So essentially it looks very similar to the automaton I've shown before for the sequence. But now instead of having only one filter edge, there's another edge down here, which we call the rebind edge. And it's doing the following. Let's assume you want to match a monotonic sequence. So you have matched expression epsilon1 up to here. Now you're looking for a monotonic sequence of increasing Microsoft stock prices. Now every time a non-Microsoft event comes in, you take that yellow filter edge, ignoring it essentially. Every time a Microsoft event comes in, you want to now, to match the monotonic sequence, you want to find a price which is above the previously found price. So rebinding essentially does, it finds the previous price, it stores it as the latest price. When a new higher price comes in, it replaces the old one by the new one. But we're still in the same state, waiting to make the transition into the final state, which could be based on another condition in addition to that sequence. Maybe you want to say the sequence should take at least 30 minutes, otherwise I'm not interested in it. So you have another, that's at theta 4 here, which is added to this edge, which is not on that one. So it might be a little tougher to get out of the state than it is to actually keep on rebinding. And notice that this is non-deterministic. So if we say we want any sequence of monotonic Microsoft stock prices of at least 30 minutes length, if the sequence keeps on increasing, we can now look at every possible sequence of length 30 or more. And each of them would be output by the automaton as a candidate to match with follow-up patterns you might be interested in. So that's a very powerful feature, which can also lead to an accumulation of instances at the follow-up states here.
So if I'm to watch for any sequence, then this automaton is going to clone, basically.
Right, so these are these instances I'm talking about. It's like a standard way of how you would implement non-determinism. So you have multiple paths you can follow. So you basically clone the automaton, and now one instance follows one path, the other instance follows the other. And it can lead, of course, to explosion of states. And so you have to be careful. But this is general. If you want that feature in the system, then you have to find a way to deal with it in the end. So that's inherent in any system that wants to support this kind of non-deterministic matching of sequences. And the other approach is that actually defined as cleany plus operator in terms of finding a maximum match, which also is a reasonable approach. So then you only get one match instead of lots of non-deterministic matches. But we thought that this operator is actually not powerful enough for many of the queries we're interested in. And last but not least, we have an aggregate operator. And it simply does the following. Say you have a tuple, an event from the stream which consists of the data fields and the timestamps. Applying that aggregate operator to that single event results in a tuple which now has an additional data field, which is the function value computed over that tuple, and the same timestamps and the same original data fields as well. So it essentially adds a new attribute to the corresponding tuple. It's the same as when you look at the SQL query. You compute an aggregate, you add it as a new column to your table of intermediate results. And now why is that actually an aggregate operator if you can only apply to a single event? Well, if you look at it together with the mu operator, in a term like this, we can actually define what people would say is a natural aggregate. So you apply an initializer function g1 on the left operand. In the mu loop, whenever you do the rebinding, you maintain the value of the aggregate. So it's functioning as an accumulator. So let's say you compute your monotonic sequence and you want to get the average cost, the average price of that sequence. Every time you rebind with a new price, you update your aggregate. And then in the end, once you're done with that mu computation, you have on the outside a finalizer, which is just taking for an average the sum and the count and divides them. And you get essentially the same as what you probably also know from SQL implementations. Just now in this kind of framework with the mu operator. So let's look at an example query and how an automaton is processing it. So I've written actually the complete query here. But actually what is important is only the pattern is the following. You start with a large sale of a stock price. Afterwards comes a sequence of price drops, of a monotonic decrease of that stock price, and then it jumps up again by 5%. So it's a very simple pattern. And there's some constants in there that determine what does it mean to be a large sale, how long is that monotonic sequence, and how big should the price jump be. But so it's probably not important right now to read the whole details of that. So the automaton looks exactly how you would expect it. We start out with a large sale to make the first transition. So theta 1 is a condition on the volume of the stocks being sold in that transaction. Then we have that mu state, which is looking for that monotonically decreasing sequence of stock prices on the same stock. So we have condition where we want to make sure that the company name is the same as the one matched before. After that, we make a transition into the new state once the duration constraint is satisfied. So we want the sequence of monotonic decrease to last for at least 10 minutes. Then we're in a new state where we're now looking for that price jump on the same stock. So we ignore all the other stocks. We look for the same company, and only if it satisfies the condition that the price is at least 1.05 times the previous minimum price, then we can make the transition to the final state and output the result. And notice that there are these renaming functions in here. So you see something like company, min p, max p. These are all original prices and the name of the company in the stock ticker values, but renamed to different attribute names in order to avoid naming conflicts. So imagine it simply, in the end what you get, you start out with a stream of events that contain name, price, and volume. I ignore for now the timestamps because they're always carried along anyways. And in this intermediate state, you have now renamed name to company and the price to max price. So now when you're in this state and the new events come in with name, volume, and price, there's no naming conflict. What does it mean? I refer to name versus price in the matched event versus name and price in the incoming event. And in the end, your schema is company, maximum price, minimum price, final price, which tells you you only need the company name once because all the sequence is on the same stock. You know the maximum that was reached in the beginning of this pattern. You know the minimum that was reached after the monotonic decrease of the price. And then you know the final price after the jump was detected in the stock sequence. And I have an example here. So instead of going through it step by step, let me just mention a few interesting parts here. So whenever there's a large stock event coming in, you can make a transition from the start state into this state. And in this state, now an instance can spend a certain amount of time because you don't have to immediately move on to the next state. So in this case, as long as there's no other stock on the same company coming in, or as long as the sequence is still monotonically decreasing, an instance waiting at this state does not have to be deleted or moved to any other state. So every time another stock makes a transition here, you might get a new instance in this state. And this is shown down here, where we have an instance for IBM and for Dell, which both made the first transition, and they're both waiting now for the corresponding future stock price values in order to make a transition to the next state once the monotonic sequence is of length 10 minutes or more. And something else to notice is when you look at this Microsoft event down here, so notice so far only IBM and Dell stock prices have arrived. Now when this IBM event arrives, you want to be able to quickly tell that none of these instances is actually interested in this IBM event because they're all on Dell and IBM patterns. So instead of going sequentially through all these instances at all these states, you want to have some way of efficiently finding those ones that are actually interested in the event and prune away all the others. So is that fairly clear up to now? And that's similar to the pub/sub problem actually. And I will talk about that right now. So now, having described how we get from algebra expressions to automata, now how can we implement it in a real system prototype? One idea would be, why don't we use standard pub/sub technology? We have a pub/sub server. We have the application server where users can register their automata or some other way to describe where they describe their expressive queries. And now this pub/sub engine is essentially sending satisfied conjuncts. So it's kind of telling you, let's say, you have some comparisons to constants in here. You take all these comparisons to constants, put them in a pub/sub engine, it does all the work for you, and you then locally in the application server keep track of in which state your current automaton is, which instances are currently active, and so on. But now if you go to a scenario where you have multiple queries, this will not be very efficient anymore, and we have some experimental results that show quite a dramatic decline in performance as soon as you add more queries in a setup like this. Now, how can we make that matching process more efficient? Well, first of all, an obvious idea is to do state merging, and that has been proposed before also for XML filtering. So you look at your automata, they all have the same start state, and then if they also have the same outgoing edges and the next state has the same incoming edges, you can actually merge automata based on their common prefixes. And this just shows that, so you have two automata, and by merging them you get now one automaton where some of the processing costs is saved because you don't have to go the same path twice again. But actually this turns out to be only one fairly minor optimization in some cases, and we found out that other optimizations are far more important in general in our system because of this parameterization and aggregates we have in the system. So what are the challenges which are different from previous pub subsystems? First of all, so now we have this big merged query DAG, this big graph of all the queries, and in this graph there might be lots of active instances at the same time. Now if an event comes in, first of all, how do we find quickly which of these edges have predicates that are satisfied by the incoming event, and also which of these instances are actually interested in the event that arrived? So in practice, we actually see that if you look, for instance, at the stock price example, if you're looking for an IBM or a Microsoft pattern, you don't care about any other stock events. So there's a lot of events that are not relevant for your pattern, and you want to efficiently prune away the search space for that case. So that's very similar to PubSub, and actually if you look at it, we also want to index predicates. So if we look back here, in order to be able to know if we make a transition or not, we have to look at the instance and its bindings it has accumulated so far. We have to look at the incoming event, and then we have to evaluate these predicates, theta 1, theta 2, theta 4, and so on, and have to determine which of them fires and which of them doesn't. And that's exactly the PubSub problem. But now it's not as easy as it might sound, because PubSub engines are only built for this kind of comparison to constants. So you can look if the name of an incoming event contains Microsoft or is equal to Microsoft. You can compare the price to a constant. But what do you do with predicates like name equals company, price greater than max price? There's no indexing approach for that. And there are basically two solutions you can take. One of them is you simply ignore these dynamic predicates. You just say, I'm good enough if I just look at the constants in my predicates, and I only evaluate, I prune enough with my PubSub index by just looking at constants. The other one is, well, at the moment when I'm actually looking if I can make a transition or not, I know all the bindings which I've accumulated so far. So whenever an instance moves to a new state, we know everything we need to know about what the value of company, what the value of max price is, and so on. And we can insert the corresponding predicate at that moment. And so we get a fairly high load on the index, of course, but we get a better selectivity of the index structure. So we decided actually to take both approaches and to be careful about where do we actually generate a high load and where we don't. And so what we do is, this is our general system architecture. So this is the system overall here. There's an event stream. The events are passed both into an FR index and an AI index combination, and I will tell you in a second what these mean. These indices produce values for matching predicates. Then we kind of have to combine the active instances that are actually relevant together with the edges that might fire, and we get all the instances that make it to a final state and produce a notification stream to the user. And in more detail how this works is, an event that is fed into the FR index, FR stands for forward and rebind. These are the edges, like the green and the purple edges, that essentially drive the advancing of instances and the rebinding of values. So this index contains all the static parts, that means all the parts of predicates which contain constants only, and puts them in a standard PubSub index. And now whenever an event comes in, this FR index tells us the IDs of all the edges of all the automata whose static predicate is satisfied by the event. So we get a superset of the actually satisfied predicates because we haven't looked at the dynamic part where we look at parameterized predicates, but we get a superset. And we have saved some computation because instead of doing it for each edge separately, we do it for all edges at once using pub/sub style optimization. AN index and AI index work the following way. The purpose of that index is to prune out those instances which are not interested in the incoming event. So the IBM pattern who is not interested in any other stock events, the Microsoft pattern that is not interested in any other stock events. This is the purpose of AN index. It first prunes out all those nodes, automata states, which have only instances that are not interested in the event at all. And this can be done based on the static part of the filter edge. So if in the filter edge it says name equals IBM, then we know every instance at that state will traverse that filter edge for that incoming non-IBM event. So we don't even have to go to any of these states at all. Similarly, the AI index now, after we've pruned out the set of nodes, we still have a lot of active instances at every state. So when we look back at the example here, when we look at this part of the processing here, at state A, we have at some point in time two instances, one trying to match an IBM pattern, another one to match a Dell pattern, and there can be many more on every company you could imagine. So there can be hundreds of thousands of active instances at this state, and if this node hasn't been pruned out because of its static part of the filter predicate, now we have to actually do some pruning on the dynamic part because we still don't want to go through all these thousands of instances which are all on different stocks. So we have another index, which is the AI index, which is local to each state, and then for each node essentially doing that pruning work for us. And then we have to get it together, so now we have the instances that can make a transition, we have the edges that could fire based on their static predicates, and now we have to join essentially these two results in order to actually know which of the instances make which transitions in the system. And there's some slides I prepared here to actually show that, but that probably would take too long to go through in detail. But it's actually fairly intuitive once you take the time to go through all these steps one after the other. But it's a fixed implementation we chose, and we're actually currently looking at how to generalize that into an optimization problem that you don't have to go with a fixed workflow like this, but could actually adaptively choose a different way depending on the selectivities of the predicates and so on, the number of instances in the system. So let me quickly show you some experimental results. First of all, to generally evaluate the performance of our system, we designed a synthetic benchmark. And out of all these parameters, what is important to realize is, so we have hundreds of thousands of queries. Each of them consists of at least 3 states. So there's a start state and then 3 follow-up states. So we have sequences of states of length 3. And there are 4 attributes that are queried on each of these transitions. And there's some of them are on continuous values, some of them are on discrete values. So we have inequality and equality predicates. And we have a zip distribution in order to determine the similarity of these different predicates, and it helps us to kind of turn the knob on how similar our different subscriptions should be in the system. So let's look at the first graph. So if you looked at query workloads or subscription workloads of increasing difficulty, essentially, the first one, linear stat, is simply you have the start state and the 3 follow-up states, and you have to make a transition on each state. There's no filter edge, there's no rebind edge. So you either make a transition or the instance dies if it doesn't match immediately on the next step. So you can imagine this is very selective and it won't match many queries, many event patterns. The second one, linear dynamic, instead of only having static predicates as the first one, it now adds some dynamic predicates where we parameterize. But otherwise it's the same simple pattern. And it turns out these two actually have almost the same performance because evaluating these dynamic bindings is not that costly in this kind of queries. The third one, which we call filter, now extends the query pattern by adding the filter edge to the different automata states. So now instances are allowed to actually wait for a while until a matching stock price comes along. So this is of course more expensive to maintain because we can have more instances accumulating in the system. And we can see that immediately the performance drops. So down here we see the number of queries in the system, the number of subscriptions. On the y-axis we have the throughput in terms of events per second. And so the throughput drops from something like 5,500 to just a little over 4,000. And with more subscriptions we see this kind of lower performance, of course. But it's not as bad as a linear decrease as one might expect. If we double the number of queries, you don't see a doubling, halving of the throughput. Then the non-deterministic workload. Now, in addition to the filter edge, we also add the rebind edge to every state. So in addition to simply having a non-deterministic automaton that can never make actually non-deterministic transitions, now we allow multiple transitions at the same time. And this, of course, adds because now new instances can be created. So we have to do much more work in the system to maintain instances. And we see immediately that also the workload has a much lower performance, or it's not that bad actually, because the query is not that big with 3 states. And the last one is the same pattern as non-deterministic before, but now we add aggregate computation. So we compute an average over the events we have matched in one of these rebind states. And that actually adds some considerable overhead as well. So there's some more results when we now look at the selectivity of the different predicates, which just show the expected behavior. So I'm just skipping over those. This one is interesting when we look at the Zipfian parameter value. The higher the Zipfian value, the more similar the queries are. And we can see that the throughput actually improves considerably because the more similar the queries are, the more we can merge them, and the more the index structures can actually prune away uninteresting events from the instances. And we can see quite a lot of improvement here by just being able to do that. But notice also that a zip of 1.4 is already quite a heavy skew. But you can imagine that, for instance, stock trading, also for blogs, there's some hot topics and people have queries that tend to ask for the same items. Now, in order to actually determine what of our multi-query optimization techniques led to the biggest improvement in performance, we actually turned on and off different parts of our system. So here we see the number of subscriptions versus the throughput. And the first curve up here is for the original Cayuga system where all the multi-query optimization is enabled. And the second line, which is basically almost the same as the first one, is for the same Cayuga system, but now we don't do state merging. So this was for a zip parameter value of 0.8, I believe. So we can see that actually in this case, if the queries are not too similar, the state merging actually has almost no effect. And notice that actually there has been quite some merging. So instead of having, I think like 100,000, for instance, for 40,000, instead of having 40,000 queries with 40,000 different first states, we have only, I believe, something like 20,000. That's about a factor of 2. And still, the performance is not much better just because of state merging. On the other hand, if we turn off either the FR index or the active node index and the active instance indices that we're doing the pruning on the predicates, on the edges, or on the instances, in both cases we see quite a heavy performance drop. And notice that the y-axis is in logarithmic scale. So we lose a factor of 100, well, let's say like 20 or 30 in performance compared to having all the features turned on. And finally, if we don't do any kind of multi-query optimization, if we do this kind of straightforward approach of having all these different queries run in separate application servers for the users, then we actually have a very bad performance, which is even below 1 event per second, which is kind of what you would expect. There's some results we have on real RSS data, but in the interest of time, I will just skip over that. They essentially show the same, that the more complex the pattern, the lower the performance. And we also compared, because we're interested in seeing what if we were using Stream or some other data stream system for this type of query processing. We looked at some stock real data, and we looked at the real query pattern, which is like an M shape, which is a pattern which is called M top or M double top pattern. And for that, we also did see that we actually, even for running a single query in our system, we got a much better performance than Stream, even for a heavily optimized query formulation. And that is due to the fact that our system is actually optimized for this kind of sequence processing compared to standard data stream systems. This just explains the queries, so I will skip over that. These are the corresponding queries from the data stream system, Stream, which are fairly complicated, and they're also heavily optimized to kind of simulate the state advancing behavior. So there are views being created that simulate kind of how we advance from one state to the next once we match a certain monotonic sequence. So to summarize, I've presented a new algebra for querying data streams in general, but actually we prefer to call it an expressive pub-sub system because it's much closer to pub-sub technology than to data stream processing. We've shown how we can take these algebra expressions, translate them into non-deterministic finite automata that support parameterization and also aggregates, and how to then implement these automata in a system efficiently to achieve high scalability even on a standard single PC. Now there are certain other issues in the system which we have addressed or we are currently addressing, and I didn't have time to talk about today. So one thing you might have noticed is that these automata are simple chains, and obviously you cannot handle arbitrary algebra expressions by having just a simple chain of states. So if we have something which is not a left-deep expression, we actually use another left-deep automaton to produce the result for a right-hand side for the right operand. And then we just feed the result of that automaton into the first left-deep automaton. So we can essentially translate an arbitrary expression into a series of left-deep expressions that are fed at higher levels of the query operator tree. Also, I only talked about how to handle conjunctions, but as long as users provide the Boolean formulas in disjunctive normal form, we can also easily handle it in our system as well, by just submitting all the conjuncts as separate queries and then putting them together later. Also, I haven't talked about how our automata handle simultaneous events, and these were these two other parameters, or there's one other parameter which I showed on the edges of the automata. So there's some kind of special handling of the filter edge which you have to do for concurrently arriving events. But it's actually fairly easy to handle once you look at the system and you process in rounds of advancing time, essentially. So you do all the events that arrived at time t before you start processing any event at time t+1. And also query rewriting, we have some initial results on rewriting queries from an arbitrary form into a left-deep expression, but we're at the start of this, and there's much work to be done still. And so in the future, we first of all, instead of having this fixed implementation, we want to have a general optimization framework where we can adaptively adjust to changes in the data stream and also the selectivity and the number of instances in the system. We want to be able to distribute the workload for an internet scale style application. We want a better query interface where you don't have to input algebra expressions but have some high-level language to actually input your queries. And it turns out we can actually also support XML filtering. So we can take XPath expressions and translate them into algebra. And by doing this, we get essentially the whole parameterization mechanism for free. So we can do things like finding elements that have the same name without having to specify the name in advance. And we also are looking at extending the functionality by adding new operators to the system to handle simultaneous events. For instance, computing aggregates over simultaneous events, because currently we're just looking at aggregates over sequences, essentially. So this concludes my talk, and I'm happy to take questions. Yes?
So for the given events, is it possible you can write different automatas? Let's say, so the order of the sum of the states is not important. You can write different automatas, just ordering the state in a different way. So how are you deciding which automata you will use to evaluate this event?
So currently our construction is the following, that if you give us an algebra expression, there's a one-to-one mapping. Well, it's not one-to-one, it's like from that algebra expression you get exactly one automaton implementation. But you can of course rewrite your algebra expression using these kind of rewrite rules that we're trying to develop also, and then you get a different algebra expression and you get a different automaton for it. And ideally you would want some framework where you can actually decide which of them is the best in order to implement it in the end. Does it answer your question?
So just another question about the merging. When you merge in the state, right? So
right.
You have a different automatas. So even the two state, it's mergeable, but the different state may require different information.
Then we don't merge them. So we only merge if they really are identical up to that point in time. So
they have identical carry-on information, then you merge them.
Right, so it's really, if you were not to merge them, they would have exactly the same instances and they would exactly look for the same events coming in at that state, essentially. So
I'm talking about the information you need to carry on.
Right.
After you pass in the state.
So if you merge, then up to that moment in time, it has to be exactly identical. And only after that, once they split into different paths, then you can start matching differently, right? You might have different predicates on the outgoing edges. But you can only merge if they're really identical. If taking them apart would essentially result in a system where just everything is duplicated exactly on these edges. So you can imagine some more aggressive way of merging, right? Where you take some predicates, take them out, and evaluate them in the end in order to make it more mergeable, or maybe allow some kind of fuzzy merging that you say, as long as the static predicates are the same, we still merge them and we do the dynamic ones separately. But it turned out in most of the approaches we thought of that this actually didn't really result in any improvement. But this was only like a theoretical analysis, so it might be actually that in practice it might be beneficial to do that.
The actual implementation you have with these indices and so on, how dependent is that on the current operators that you have? Is that sort of an implementation that supports exactly the operators that you currently have, or does it generalize from there? If you have a more general algebra, what happens with this machinery?
Yes, as long as you can formalize it in terms of these automata, where you make state transitions based on predicates being satisfied or not, then it should fit into the same optimization framework, that you can have the same type of index structures. But of course that's the tricky part, right? So if you come up with a complicated operator, it might not be possible to have an automaton that can actually implement that type of operator. And so it took us a while also to figure out what you can do in terms of expressiveness so that you still are able to do this kind of optimization in pub/sub style. So if you did some arbitrary kind of window joins, for instance, or like what Stream is doing, you can actually have all the events that arrive at the same time and can do arbitrary computations by just mapping it essentially into a relation and then running relational algebra on it. Then you might be not able to actually have an automaton that can do this kind of state advancing the same way we want it to be. Okay, so if there are no more questions. I'm also available offline after the talk, so if there are any questions about the details. Okay, thank you.